All right, so this is the last of the three examples that I showed you. This is the example of a inconsistent system of three equations. And it's just a bit of a weird one because I actually omitted x. I kind of put together this example because it was easy for the visualization, right? To show you like what the graphs look like when the three planes don't intersect each other. But I didn't use x in any of these equations. So you may remember, well, you may be thinking like, well, if there's actually only two variables, why are we talking about, planes in three-dimensional space? And there's something I kind of neglected to tell you, which is that sometimes you can have an equation that has fewer variables, but you can still consider its solution set in any dimensional space that you want. So, like, for example, just a quick little example down here, in two-dimensional xy space, right, like where you graph equations with two variables, you can also look at an equation with a single variable, like, for example, x equals 2, right? X equals 2 is an equation with a single variable, and so you could plot its solution on a number line, it would just be 2. But you can also consider that as describing a line in two-dimensional space. It's just a vertical line, right? It doesn't really have any dependence on the y coordinates at all. It just is this vertical line. It's all the points in space that have x equal to 2. So these equations up here that involve only y and z, they can still be thought of as describing planes in like x, y, z three-dimensional space. Those planes just are kind of parallel to the x-axis in a way. So the explanation for why this is inconsistent is actually really quick. We already have z equals 3, right? So what we can do is substitute that back into the second equation and get y minus 3 equals negative 2. Add 3 to both sides, and we'll have y equals 1, right? So now, substituting both the z equals 3 and the y equals 1 back into equation 1, we'll get 1 plus 3 equals 1, which says 4 equals 1, right? Well, that's false. So like in the two-dimensional, two-variable case with the inconsistent example, we ended up boiling it down to just a false statement, right? Like one number equals a different number. And so that means that the system of three equations has an inherent contradiction in it, which means the three equations can't ever be true at the same time, and therefore there's no point, no combination of variable values that is going to solve all three of these equations at once. So, inconsistent. No solution.